Hello there, students. Today, we're going to learn about the dot or scalar product. In the previous video, we discovered quite a few ways we can multiply vectors with other vectors. The first one we saw was the dot or scalar product. Let's see what this was all about. This first type of multiplication is called the dot or scalar product. It has this name because we symbolize this operation with a dot, and the result of the multiplication is a scalar. To figure out the result of a dot product, or the scalar, we follow one of two equations. As an example, consider two vectors, vector A and vector B. To be completely general, we can write out a generic vector as having components like this, where vector A has variables as their x and y components, written as a sub x and a sub y. The same goes for vector B. We can also draw these vectors here. If we put the two tails of these vectors together, we see that they can in general be separated by an angle theta. Both vector A and vector B also have their own magnitudes shown here. Now that we can see all the variables and the visual representation, let's look at the two equations that define the dot or scalar product. Which equation we use depends on what information we have about the vectors in the product, though both are mathematically equivalent. As you can see, if we know the vector components of each vector, then this equation is more practical to use. However, if we only know the vector magnitudes and the angle separating the vectors, then this other equation is more useful. Because they are equal though, we can always move between the two equations. If we take a closer look at the second equation, the one with the cosine term, we know that cosine can take any value between -1 and 1, including 0. This means a dot product could be equal to 0, if, for instance, the angle theta we put in the cosine term is 90 degrees. Let's take a look at the vectors that are joined at their tails again. If we have a flashlight and put it above both of these vectors in the y direction, and point it straight down so that it's facing perpendicular to vector B, we can see that vector A will cast a shadow onto vector B. The size of that shadow is related to the scalar result of this dot product. Let's see why that is. Let's consider that angle theta of 90 degrees again. This means vector A and vector B are perpendicular to each other, like this. Again, we know that the cosine of 90 degrees is 0. If we imagine our flashlight shining on vector A from above, we see that there is indeed 0 shadow. We can also see this by looking at the other equation for a dot product which uses the components. When arranged this way, at 90 degrees to each other, we see that one vector has only a y component, and the other vector only has an x component. So when we plug these into the equations, we see we get something times 0 plus something times 0. This is always equal to 0. By the way, this equation was written for our vectors which are in 2 dimensions. If we wanted to write the more general 3-dimensional equation for a dot product, we just need to include the z components like this. The maximum value for this scalar product, or size of the shadow, is when the two vectors are parallel to each other. This is when the cosine term equals to 1 if the vectors are parallel, or -1 if they are anti-parallel. We'll do a few more examples using dot products at the end of this playlist after we've learned about the cross or vector products in the next video. One last note about dot or scalar products. In some courses, you might see this type of product called an inner product. This is something you'd probably see in a linear algebra course when talking about vector spaces. Thanks for watching and learning about vectors. If you have any questions, feel free to leave a comment or head over to my Facebook page in the video description and post a question.